up to 1, and every probability is between 0. Yesterday we talked about discrete versus continuous. Discrete is when you can count every possible value. Continuous is when there's an infinite number of values. So we can really only make those tables if it's discrete. Then we saw some cases where we had a set number of trials and some where we didn't. So if I said I'm going to flip a coin 10 times and count how many heads I get, there's a set number of times that I'm going to flip that coin. But if I said I'm going to flip a coin until I get 10 heads, do I know the maximum number of times I'll flip my coin? No. So in the case where we have discrete data and only 2 possible outcomes and a fixed number of trials, then we can have what's called a binomial. So the key is here. You have to have a fixed number of trials. If I don't know how many times I'm going to flip it, it's not binomial. They're independent. The probability can't change each time. So if I'm going to draw a card, I would have to look at my card and then put it back in the deck before I drew the second one. If I'm taking a card out each time and not putting it back, every probability is different. So it has to be independent. For it to be binomial, there are only 2 possible outcomes, success or failure. So if I'm rolling my dice and I want to see how many heads I get, a success would be heads, a failure would be tails. If I'm drawing 10 cards and I want to see how many times I get an ace, ace would be success, not an ace would be failure. I can't have more than 2 options. And we have to have the same probability of success each time, which kind of goes hand in hand with it being independent. So if I were drawing for my aces, I have to put my card back, so my probability doesn't change. So first, let's look at these and see if they'd be binomial. A player rolls a fair die 10 times. The number x of 7 rolled is recorded. So do I have a fixed number of trials? Yes. Are they independent? Yes. What I roll one time doesn't change what I roll the next. Do I have 2 possible outcomes? Since I'm only worried about the number of 7s, my outcomes would be 7 or not a 7. I'm not counting how many times I get each number. And the probability of getting a 7 is the same each time? Yes, so this is binomial. We'll talk about like N, P, and Q a lot with this. N is the number of trials, so there's 10. P is the probability of a success. So if we were looking at, we have a pair of dice, we'd have 2 dice, so we would have to figure out how many times they would add up to 7 and get that. So P is the probability of success. And Q is typically called the probability of failure. So B, an official with the FAA randomly selects airline flights until she finds 10 that were not on time. The number of flights X that need to be selected is recorded. So is this one binomial? No. Why?
It's not a fixed number of trials.
C. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number of females selected is recorded. So we're selecting 4, so it's a fixed number of trials. Okay, are they independent? No. I can't pick the same person 4 times. If I'm picking 4, once I pick that first person, the probability changes for the next one. So this one is no, they are not independent. All right. Smells good for about 10 minutes. And then, 2 hours later it does not. So the 11 largest air carriers had an on-time percentage of 79% in May 2008. Suppose that 4 flights are randomly selected from May 2008 and the number of on-time flights is recorded. Construct a probability distribution for the random variable x using a tree diagram. So we haven't done a tree diagram in a while. We are going to select 4 flights. And so our 2 options, we have success or failure, on time or not on time, right? So the first flight. My first flight, there's 1 of 2 options. Either they're on time or they're not. And then for my second flight, there's 2 options. So it could have been the first one's on time and the second one is on time, or the first one's on time and the second one is not. Or first one on not, second one is, or they're both not. Do you guys see how this tree diagram is branching out? Okay, we need to do 4 flights, so the third. So for each of these, we have another branch coming off. And then we have our fourth flight. So the tree diagram is really just a way of looking at every possible outcome. Everyone okay with how we got that? So I asked you for the probability distribution. What is a probability distribution? When we list each x and its probability. All right, so x in this case, what am I counting? Okay, so my possible values for x would be what? 4, 3. Okay. So if I'm trying to find the probability of each of these things, we have to look, how many outcomes did we end up with? 16? All right, so for no flights to be on time, so I'm looking failure, 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 failure. How many times did that happen? 1 out of 16. So we get a probability of then for 1 flight to be on time. So we have to count the different ways that could happen. So it could be the first one, but then none of the others. It could have been the first one wasn't, the second one was, and then none of the others. Or the first and second weren't, third was, and not the last one. Or these 3 were not, and the last one is. How many different options have 1 flight on time? 4 out of 16. Okay, so that is 0.25. Okay, but we've kind of oversimplified this a little bit. When I'm looking at this, what have I not taken into consideration? Look back at the original problem. There was some other information given in this problem that we haven't used. Yeah, what's the 79 have to do with it? that was the percentage time. Is this a 50-50 shot? No. So is what we're doing actually accurate? No, we've found all the possibilities, but this isn't using the fact that we know it's not just flipping a coin. So it becomes more complicated than this. All right, we have to go back and think, well, all right, if there's 0 flights on time, okay, here's how that happened. What's the probability that a flight was not on time? If there is a 79% chance that it's on time, the probability that it's not on time is 21%. Okay, so a lot of times we call P, the probability of success, is 0.79. The probability of a failure is often called Q, is 0.21. We are looking for 4 times. So if I am not on time 4 different times, the probability of not being on time is 0.21, and that happened 4 times. So what's 0.21 to the 4th? Okay, so that probability really turns into 0.00194. All right, so for one flight being on time, we found that there are 4 different times this could happen, right? So for any given time, one flight was on time. What's the probability of that flight being on time? So that happened once. So then we had 3 flights that were not on time. And we saw this was 4 different times in our chart this occurred. So if we took it times 4, we get 0.02926. And why did I take it times 4? 4 times in my table. 4 out of the 16 times this happened. 1 flight was on time, 3 were not. Okay, for 2 to be on time. So the probability of being on time is 0.79. That happened twice. So that meant 2 of them were not. So that happened twice. So now you have to go back and count. How many of them have 2 on time and 1 not? So it could be like the first 2 are, second 2 not. First. So how many do we get? 6. So 6 times this happened. 6 times 0.79 squared times 0.21 to the second. And we get 0.16514. All right, 3 flights being on time. So that means 3 were on time, so 0.79 to the third. 1 was not, so 0.21 to the first. And then we need to count. How many different ways does that occur? So it could be like the first 3 are, the last 1 not. So how many options do we get for this one? 4 of them. All right, and the last one, all 4 on time. How many times does that happen? Only once. Probability being on time is 0.79. That was all 4 of my flights. You get 0.38950. Okay, so is this probability model? Is every probability between 0 and 1? They add up to 1, maybe with a little rounding error. But this got pretty complicated, didn't it? We weren't anymore just looking at how many total outcomes because the probability of each step along the way was different. So it's nice if we have a shortcut for this. And there actually is a formula for how to find these. So our probability is n choose x, p to the x, 1 minus p to the n minus x power. Right, if you look on your formula sheet, we're in chapter 6, binomial probability distribution. All right, so in choose x, this is a counting feature on our calculator. There's a formula for it. You probably saw it in algebra 2 at the very end. You probably did some basic probability stuff. That's where these numbers came from. We had 1 of these, 4 of these, 6, 4, 1. So those numbers come from the n choose x. P was the probability of success. Okay, this one, my n choose x is 1.
If you like black coffee, you can actually add that.
We had no flights on time. We had 4 that were not. Okay, so you'll notice my x was 0, so that's a 0. N minus x, we had 4 flights, so if none were on time, that meant all 4 were late. If you go to your calculator, let's see if we can check our work. All right, to do the n choose x, first open a parenthesis. N, how many flights were we looking at? 4. Then if you go into math, over to probability, and then third one, NCR. So these calculators that you have one of mine, it looks a little bit different. It doesn't put them as subscripts, but it's the same thing. So we had 4 if I want 0 to be on time. Then it's P. So P, the probability of success was 0.79 to the x power, which was 0 flights. 1 minus P, 1 minus 0.79 is 0.21. To the n minus x, 4 minus 0 is 4. And if we do that, is that the same probability we had for 0? Yeah. And if we went back and we changed it, okay, now if I want 1 flight on time, then it would be 4, choose 1. Then I have 1 success, so it would be 0.79 to the first. And if 1 was on time, then that meant only 3 could be late. So then this would be to the third. And did that give me my second one? Yes. So this is a much faster option. Okay. According to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, what is the probability that exactly 5 have 3 or more cars? So first, what is my n? How many are we looking at in our sample? Okay, and then we need P. The probability of success is? Right. So on A, I want exactly 5. So when I type this in, I'm doing parentheses 20, choose 5. So that means I have 5 successes. So 0.35 to the 5th. 1 minus 0.35 is 0.65. Okay, if I have 5 that did, how many didn't? 15. 20 minus 5. Mm-hmm.
Where did we get 0.65 from?
1 minus 0.35. And what do you get?
I did not.
All right. What is the probability that less than 4 have 3 or more cars? So what would I have to add up? 0, 1, 2, and 3. Okay, kind of annoying, but we can do it. So we need 0, 1, 2, and 3, which I already found. Oh no, I didn't, never mind, we did 5. So I have to add these up. Okay, so if you just hit second enter, we're going to do 20 choose 0, 0.35 to the 0, so it would make 0.65 to the 20th. Okay, you'll notice at the end it has e negative 4. What does that mean? Moves the decimal back 4. So then to get 1, if you hit second enter, bring it back up, now we want 20 choose 1. 0.35 to the first, 0.65 to the 19th. And then we change our x to a 2. And then a 3. So then if we add those all up, get about 0.0444 if we round to 4 decimals. Does everybody understand how I got that? Okay, I want to show you something. On your formula sheet, go to like the 4th piece of paper. This is a binomial table. It does not have all of these options because it can't have every possible n and probability. It would just be a ridiculous amount of paper. However, it has some. So you'll notice across the top, these are the probabilities. That's your probability of success. What was the probability of success in this problem? 0.35. So we could go to the 0.35 column. My n, we were looking when n is 4. So you see out here we have like sections. So we would go down to when n is 4. And then you see it's got the x column. So it's a lot of tables to read through. But if we look at this, we want the 0.35 when n is 4. And if you look, then it has the probability of 0s, 1s, 2s, 3s, 4s. So it can give us a lot of our probabilities here as well. Okay, so the downside of this is it doesn't work for, wait, we didn't have 4, we had 20. Sorry, I was thinking the previous example. Go to, we've got 20, back page. Because, right, we had 20 in our sample for our n. I was thinking back to the 4 airplanes again. So 0.35, when my n was 20, we had 0, 1, 2, and 3. If you add those up, do those, or if you look at those, are those pretty similar to what we wrote down, rounded to 4 decimal places? You'll notice sometimes on the table you might see something like a bunch of zeros and a plus. That means the first 4 digits are all 0, but there's some digits after that. So you can use this table for the ones that are on here. So the next one Next example says, what's the probability that at least 4? What would that mean? 4 or more. So we could do it a couple different ways. We could go to our table and add up on the 0.35, 4 or more, or what would be the easier option rather than adding all those numbers? 1 minus what we already found, because those are complements. We get 0.9556. D, what's the probability between 3 and 5 have 3 or more cards? So let's try our table for this. So when my probability is 0.35, my n is 20. I want to add up when x is 3, 4, or 5. So when our x is 3, what is the probability from this table? Plus, when x is 4 on the table, it says, and 5. So if you add those all up, if you had done them by hand, your answer might be slightly different because of rounding. This table rounds everything to 4 decimal places, so there is that chance. So does everyone understand how to do it by hand and from the table? You can't only do the table because I'm guaranteed to give you some probability that's not on here at some point. So you have to be able to use your formula. I think we're going to do one more example and then I'm going to stop for today. The mean and standard deviation for the binomial are actually pretty easy to calculate. Mean is n times p, and standard deviation is the square root of n times p times 1 minus p. Just like everything else that's on our formula sheet. So if I wanted the mean and standard deviation in this scenario, we have 35% of all car-owning households have 3 or more cars, so that's my p, probability of success. And a random sample of 400, so that would be my n. Find the mean and standard deviation. So my mean, n times p, 400 times 0.35. Standard deviation, square root of n times p times 1 minus p. 400 times 0.35 times 1 minus 0.35. .5394. I'm stopping here for today. Tomorrow we'll finish it up and I may throw in a couple more review problems. So homework will not be due until Thursday. Just like all the others, if the question on number 35 it says to interpret every probability, you don't have to, but make sure you could if I did ask you.